Hello and welcome to video lesson 16 on combined stresses. This is part 2 of our session on combined stresses. And this is where we're going to work a practical example where some of these components of the 3D stress tensor or the 2D simplifications are built up from some of the simple solutions that we have learned about so far in the class. So for this particular example, I've got a simple shaft that is attached to a fixed support. I'm interested in the stresses at 2 points at the fixed support, which are good candidates for extreme stress in the entire shaft. Well, you might ask, well, where might I run into a problem like this? And the answer is really one a little bit, maybe a little bit more for the mechanicals. You could imagine this shaft being the shaft that would support a helicopter blade, and you might have, you would definitely have torsion as you're spinning up the helicopter as the blade is accelerating angularly if the pilot needed to make a speed change. You would have some axial force as the helicopter's shaft is going to suspend the cab. You would also have the potential for flexure and transverse shear as a result of lift forces on the blade of the helicopter. So you could have a helicopter shaft, for instance, that would be subjected to many of these same types of loadings. So we would need to be able to make some sense out of the state of stress at important points along the shaft so we could maybe evaluate whether that shaft design was going to be acceptable or whether it was not going to be acceptable. So we've got on our shaft here, we've got a 2,000-pound tension, and I've got a 1,000-pound force applied with an eccentricity of 10 inches about the center of the shaft. So it's got a force component and a moment component, and we can think about this particular force being replaced by an equivalent force couple system. And I'm going to just show these in dashes because they're the same thing together as this 1,000 pound force. So V here would be equal to 1,000 pounds. And the torque that's going to cause torsion in the shaft would be 1,000 pounds times 10 inches or 10,000 inch pounds. And then, of course, I've got P equal to 2,000 pounds, like so. If I was to take a look at the statics of the problem, I would have a moment reaction, so there would be some bending. And I'm going to get moment because I've got a shear or a vertical force applied here, and it's got a 20 inch moment arm. So M is 20,000 inch pounds. So to help you visualize and sum up what's going on, we've got axial loading, we've got a shear loading, we've got a torsional loading, and we end up with a flexural load because V is going to create a bending moment. And with the bending, A is going to be on the compression side, so it's going to be crushing as a result of this force. So let's see if we can visualize what's going to happen at point A and point B. So point A would have axial stress, due to the 2,000 pound axial load, and that's going to be given as P over A. Point A is also going to be compressing as a result of bending the shaft this way as a result of the force V. So, so as point A is at the most extreme point, we would have the formula MC over I, but it's going to be compressive, so it's going to push in on the X face of our element. And our torsional loading is going to create a torsional stress of magnitude TC over J. Once again, we're at the extreme point on the boundary of the shaft. However, since the transverse shear is applied in the vertical direction and point A is at the very top of the shaft vertically, there is no transverse shear because Q would have to be 0 because there is no area above A. There is no area above point A, so we have to take that into account. So there is no transverse shear at location A. Now at point B, we would have axial stress due to the 2,000 pound axial load. We wouldn't have any flexural stress, though, because point B is located at the neutral axis. We do, however, have transverse shear stress develop as a result of the 1,000 pound force. And we do have a torsional shearing stress that's going to be the result of this torque. And now it is important to note that the torsion is going to twist counterclockwise, but at point B, so if the torsion twists counterclockwise, at B, the shearing stress is going to be downward. But the transverse shear is going to be upward because the loading is upward. So we have those two shearing stresses acting in opposite senses, and I've drawn that here. So I've got TC over J coming down and VQ over IT coming up. And then, because I know shearing stresses are always complementary, the shearing stresses have to be drawn equal on the Z face in the X direction, the X face in the Z direction. So TC over J on both of these faces for point A. And then I've got BQ over IT, both drawn acting toward that line, and then TC over J, both drawn acting away from this line. So I have complementarity in all of my shear stresses. Let's figure out what those stresses are. So for the stresses at point A, I would have sigma XX equal to P over A minus MC over I. P over A being positive because it's in tension, MC over I being negative because it's in compression. And then this is a straightforward computation, 2,000 pounds for P, pi over 4 times the diameter squared for the area, minus 1,000 pounds times 20 inches, which is the bending moment, times C, which would be, 1,000 pounds times 20 inches, which would be 20,000 inch pounds, times C, which would be 1 inch, divided by I, which would be pi over 4 times d to the 4th. And that would give me a stress of negative 24,828 pounds per square inch, and that would be a compressive stress. So just to help clarify, this is M, this is C, and and this is I. And I for a circle is pi over 4 d to the 4th. So if I was to calculate the shear stress, the only shearing stress that I would have at point A is the torsional shear stress. And that would be given to me as TC over J. And we talked about earlier our torque of 10,000 inch-pounds, 1,000 pounds times 10 inches would be how we would get that number, times 1 inch, which would be C, and then J is pi over 2 times 1 inch to the 4th. And that gives a shearing stress of 6,369 PSI. So if I was to represent this on a 3D element, I'm going to only draw one side of the element. So the stresses here, tau Zx would be 6,369 PSI, tau Xz would be the same thing, it would be 6,369 PSI. And then sigma XX is negative 24,828 PSI. And if I was to take a look at the top view of the element, I would see this. I would take a look at the X direction going this way, the Z direction being positive this way. And I would have a plane stress simplification because the only stresses that are active on this problem are in this same plane. So if I was to draw the stresses on the plane, I would have this case right here, and I do actually have a plane stress situation because the only stresses that I would have would be tau XZ, sigma XX, and sigma ZZ, but sigma ZZ is 0. So all of these stresses are in the plane, and if I take a look at this and I rotate my paper to the side like this, you'll see the positive convention here for the shear stress, and this would be a negative number for compression. So that should explain to you how we would get a plane stress simplification, and we'll see later on in the lessons that plane stress simplification allows us to investigate a lot of important things for practical problems. Let's do the same thing at point B. For point B, sigma XX equals P over A. And that would be the only thing causing axial stress in the X direction, just this P. We don't have any flexural stresses at point B because point B is at the neutral axis. So all we have for the stresses at point B is sigma XX equals P over A, and that's 2,000 pounds divided by pi over 4 times 2 inches squared. And that gives me a result of 637 PSI. For tau XY, I'm going to take advantage of the fact that I have a circular cross section, and I'll take the maximum transverse shear in the circular shaft as 4B over 3A. We talked about that formula in our video on transverse shear. And we're going to talk about, and then we're going to take away TC over J because it's acting in a sense opposite of the transverse shear stress. So what we would have at this particular point is 4 times 1,000 pounds for 4B over 3A, 3 times pi over 4 times 2 inches squared, minus TC over J. Well, we computed that up here, 6,369 PSI, and that leaves us with 5,944 PSI. Well, which point fails first? Well, we would expect that this would be the point that would fail first because we have numbers that are significantly larger, but we've got two stresses that we're concerned about. And if these were a little bit closer together, we might have some trouble distinguishing which point would fail first. And even beyond that, since we've got multiple stresses, we might not be sure whether either point would fail at all in yielding or some other kind of stress. So we would want to stay tuned for a later lesson to be able to fully make sense out of these numbers. So just keep in mind that we have got a further lesson that's going to be necessary to make full sense out of all of this. So if I was to draw the stresses here on the 3D cube and do the 3D representation of the stress tensor at point B, I'd have sigma xx is positive 637 psi because that's a tensile stress. And then I would have complementary shear stresses that have to be equal, but the couple moments have to act in the opposite sense about the center of the cube, which is located at point B. And if I was to just view this where the z-axis is coming out of the board, I could once again have a plane stress simplification, and I would have sigma xx equal to 637 psi, and then tau xy equals tau yx equals 5944 psi. So that's all for video lesson 16.